This video is on truth tables. It is part 2 of 3. I will link the first video in the description of this video. So we said last time in that video that truth tables can do 3 things for us. They can help us categorize the truth conditions of sentences. And in this video, as we will see, they can help us determine whether an argument is valid or invalid. What does it mean for an argument to be valid? We have a definition here. An argument is valid if and only if it follows a proper deductive form. In other words, if the truth of the premises guarantees the truth of the conclusion. We're going to have a second part to that definition that deals with truth tables. An argument is valid if and only if, in a truth table, in every row in which all of the premises get a T, the conclusion gets a T as well. And we'll see what that means later on in the video. Of course, then, what does it mean for an argument to be invalid? An argument is invalid if and only if it does not follow a proper deductive form. In other words, it is possible for the premises to be true and the conclusion to be false. The second part of that definition, an argument is invalid if and only if, in a truth table, there is at least one row in which all the premises get a T, but the conclusion gets an F. And again, we will see what that means once we do some truth tables. Don't forget, we have our 5 rules here that correspond to our 5 operators: conjunction, disjunction, conditional, biconditional, negation. You should try to have these 5 rules memorized. Also, don't forget, what are the 3 steps for completing a truth table? You have to set it up, you have to fill it in, and then you have to evaluate it. Okay, so let's do our first truth table. Again, we're doing truth tables in this video to try to determine whether or not arguments are valid or invalid. So we have our first example here, premise 1, if P then Q, premise 2, not Q, conclusion not P. Is this valid? Is this invalid? Let's see. We got to set up our truth table. We draw our cross. In the upper right-hand corner, we have all of our premises and our conclusion. As you can see, we've kept each premise and the conclusion away from one another. We have to keep them individualized. When we fill in our truth table, that will make a big difference. Upper left-hand corner, we have every simple sentence that falls into our complex sentences that make up our argument, and then the lower left-hand corner, every possibility of truth and falsity. Now we have to fill in our truth table. We're going to fill in each premise and the conclusion separately, so let's start from left to right. Our first premise, premise 1 here, it's just a simple conditional. If P then Q. A conditional is only false when you have a true antecedent and a false consequent, line 2. So that's just going to be true, false, true, true. Premise 2, not Q. That's pretty simple. You just take the Q column and we flip it. And then we do the same thing for the conclusion. Not P, we just take the P column and we flip that. So true, true, false, false becomes false, false, true, true. Now we have to evaluate what we have here. Now, for each one of these premises and the conclusion, there's only one operator. So we don't have to ignore any columns. We only care about the main operator. But in this case, every sentence only has one operator, so we just focus in on those 3 operators. Now we have to answer the question, does the truth of the premises guarantees the truth of the conclusion? In other words, every time that the premises are true, is the conclusion true as well? So what we have to look at is every row, from left to right, every row in which all the premises are true. So ignore the conclusion column for now. Look at every row in which all the premises are true. That's the only rows that we care about. We don't care about row 1 because in row 1 at least one premise is false. Same thing for 2, same thing for 3. The only row that we care about is 4. So we don't care about 1, 2, or 3. You can literally just cross those off. We don't care about those. We only care about every row in which all the premises are true. In this case, premise 1 and premise 2. Because remember what it means for an argument to be valid. If the premises are true, the conclusion has to be true. It's a conditional promise. So we only care about when all of the premises are true. Like, again, in line 4. And yes, even though there's only one of them, in every row in which all the premises are true, the conclusion is true as well. So this argument is valid, or this argument form is valid. Here's another example. Premise 1, if P then Q. Premise 2, not P. Conclusion, not Q. Same thing, set up our truth table here. For our cross, upper right-hand corner, we have our premises and our conclusion separated. Upper left-hand corner, every simple sentence that appears in those complex sentences. Lower left-hand corner, every possibility. Premise 1 is a conditional. It's only false when you have a true antecedent and a false consequent. So it is true, false, true, true. Not P, you just take the P column and you flip it. True, true, false, false becomes false, false, true, true. And then the Q column, true, false, becomes false, true, false, true. Now we have to evaluate our truth tables. Again, we don't have any extra operators to worry about. We only have a main operator in all of our sentences here in premise 1, premise 2, and the conclusion. So we focus in on those columns. And remember, we want to know if the premises are true, does that mean that the conclusion will be true as well? So we only care about all of the rows in which all of the premises are true. We ignore the conclusion column for now, and we look at every row in which all the premises are true. In row 1, we have a false premise, so we don't care about row 1. In row 2, both of the premises are false, so we don't care about that. But we do care about 3 and 4. Look, in 3, both of the premises are true, and then in 4, both of the premises are true, so we do care about rows 3 and 4. But as you notice, there is at least one row in which all the premises are true, but the conclusion is false. In other words, there's at least one row in which the premises get a T, but the conclusion gets an F. Yes, there is also a row where the premises are true, where the premises get a T, and the conclusion gets a T, but that kind of doesn't matter. As long as there is one row in which the premises get a T and the conclusion gets an F, that means that the whole argument is invalid, or the whole argument form is invalid. And let's be really clear, it's not that it's valid in 4 and invalid in 3. The existence of 3, in which there's at least one row in which the premises get a T, all the premises get a T, but the conclusion gets an F, that one row shows that the whole thing is invalid, because that one row shows that there's no guarantee. It is possible for the premises to be true and the conclusion to be false. Even if it's also possible for the premises to be true and the conclusion to be true as well, that doesn't matter. Because it's possible for the premises to be true and the conclusion to be false, like line 3 shows, that means that it's invalid, because that means that there's no guarantee. It is not the case that the truth of the premises guarantees the truth of the conclusion. Here's another example. It's going to be a little bit more complicated. If P, then Q and not R, premise 2. If Q, then R, and then the conclusion, not P. But it's going to be similar, that we're going to set up our truth table in the same way. Draw our cross. The upper right-hand corner has the premises and the conclusion. The upper left-hand corner has every simple sentence that appears in those complex sentences. And the lower left-hand corner has every possibility in regard to the truth and falsity of those sentences. Okay, this is going to take us a little bit more time to fill in. That's all right. Premise 1 is fairly complicated. Remember, we have to start from the inside of the parentheses to the outside of the parentheses. So we actually have to start with not R. We start with the not R column. And every time R is true, not R is false, and vice versa. Now we can fill in the conjunction. The conjunction is a conjunction of Q and not R. So you look at the Q column, and you look at the not R column, and you apply the rule, a conjunction is only true when both conjuncts are true. In this case, it looks like lines 2 and 6. Now we can fill in the conditional column. In the conditional, the antecedent is P. The consequent is that column that we just filled in, the conjunction. So we apply the rule, a conditional is only false when you have a true antecedent and a false consequent, like in lines 1, 3, and 4. Every other time, the conditional is true. Now we can move on to premise 2, if Q then R. This is a little bit more simple. A conditional is only false when you have a true antecedent and a false consequent. So you look at the Q column, you look at the R column, and you apply that rule. Only false when Q is true and R is false, like in lines 2 and 6. And now the conclusion column, not P, that's fairly straightforward. True, 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 false, 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 just becomes 4 falses and 4 trues. Now we can evaluate our truth table. In this example, we do have some columns that we're not going to get rid of, but we can ignore. We only got these columns over here, the conjunction and the negation column, so that we could get the conditional column. The conditional is the quote-unquote main operator. So we only care about that main operator column. And we don't care about the other two. These are the main operator columns. These are the columns that we care about, that matter for us in evaluating our truth table. And also, we don't care about every row, right? We only care about all of the rows where all of the premises are true. Ignoring the conclusion column, where are all of the premises true? It looks like 5, 7, and 8 are the rows where all the premises are true. In every other row, at least one of the premises is false, so we don't care about those rows. We only care about the rows in which all of the premises are true. 5, 7, and 8. And as we see, in 5, 7, and 8, the conclusion is true as well. So, in every row in which all the premises get a t, the conclusion gets a t as well. So, this is a valid argument. Here's another example. Premise 1, not p. Premise 2, not q. Premise 3, if p, then not q or r. And the conclusion here is not r. Fairly complicated argument, at least compared to our initial examples, but we can still do it. Let's set up our truth table, draw our cross. Upper right-hand corner, we have all the premises and the conclusion. Upper left-hand corner, every simple sentence that appears in those complex sentences. And lower left-hand corner, every possibility of truth and falsity in regard to P, Q, and R. Now we can fill in our truth table. Premise 1, premise 2, those are going to be pretty simple, right? You just take the P column and you flip it. Premise 2, you just take the not Q column and you flip it. Premise 3 is going to take a little bit more work, right? We have a conditional, a negation, and a disjunction, right? We have to start from the inside and work our way out. So we'll start with not Q. That's pretty simple. Again, you just take the Q column, true, true, false, false, true, true, false, false, and you flip it. It becomes false, false, true, true, false, false, true, true. Now the disjunction here, it's a disjunction of not Q and R. So you take the not Q column and R and you apply the rule. A disjunction is only false when both disjuncts are false. In this case, it looks like 2 and 6. Every other time, at least one of the disjuncts is true. And now we fill in the conditional. The antecedent is P. The consequent is the disjunction here. And it's only false when the antecedent, P, is true, and the consequent, the disjunction, is false. Only true when the antecedent is true and the consequent is false. Like in line 2, in every other row, it's true. Now we can fill in the conclusion, not R. That is simple as well. You take the R column. Every time R is true, not R is false, and vice versa. Now we just have to evaluate our truth table. Again, we don't care about the negation column here. We don't care about the or column here. We only got those so we could get this. Right? We don't care about any column that's not a main operator column. We only care about the main operators. So we can kind of ignore those too. And then we can cross out some rows as well. We ignore the conclusion column, and we only care about the rows in which all of the premises are true. In what rows are all of the premises true? Not 1, or 2, or 3, or 4, or 5, or 6. In 1 through 6, at least one of the premises is false. But in 7 and 8, all of the premises, premise 1, 2, and 3, are true. So we do care about 7 and 8. But we don't care about the rest. But as you look over here, there's at least one row in which all the premises get a T, in which all the premises are true, but the conclusion gets an F. The conclusion is false. So this argument is invalid. And I'll restate it one more time. It's not that it's invalid in 7 and valid in 8. It's that the existence of 7, where all the premises are true but the conclusion is false, that one row shows that the whole thing is invalid. because that one row shows that there's no guarantee. It is possible for the premises to be true and the conclusion to be false. That's what 7 shows, so 7 shows that the whole thing is invalid. One more somewhat simple example. Set up our truth table like we've done. Fill it in. A disjunction is only false when both disjuncts are false, like in line 4. Not Q, that's simple enough. You take the Q column and you flip it every time Q is false, not Q is true, and vice versa. And now for the conclusion. The conclusion doesn't have any operators. The conclusion is just P, but it would probably help you to get the information from over here to over here, just visually. It might help you. So you literally just take this column and you just supplant it under the conclusion P. I guess you don't have to do that, but it might be helpful to you because you're literally just transferring the information from here to here, but it could be helpful. And then we have to evaluate. Now we do have some rows to ignore. We only care about the rows in which all the premises are true. If there's a row with at least one false premise, we do not care about that row. We ignore our conclusion column and we look over here. What are the rows in which all the premises are true? It looks like only 2, so we don't care about 1, 3, or 4. And there's only one of them, but in every row in which all the premises are true, again, even though there's only one of them, the conclusion is true as well. In every row in which all the premises get a T, the conclusion gets a T as well. So this argument is valid. Here are some examples for you to try on your own. If you want to pause the video and try them and then see if you got the correct answer. Here's the truth table set up. Here it is filled in. And here it is evaluated. Another example. The truth table is set up. Here it is filled in. And here it is evaluated. Set up, filled in, evaluated. Again, this is the type of thing you might not get at the first try. If you have to go back and watch this video a couple more times, you would not be alone. A lot of people have to do that. So yeah, give it a try.